Hello and welcome to Lecture 3 of Measurement and Uncertainty. We're going to look at how you take a set of measurements of a single quantity and get a best estimate of that thing you're trying to measure and an error estimate, an uncertainty estimate. There is a document in the lab manual files on Moodle which does all of this in a little bit more detail, and that'll be a useful reference document for you when you're actually working in the lab. So you should get to know your way around that document. So it's called Introduction to Measurement Uncertainty, and you should really read it. So suppose we have measured the height of a door. And we're trying to do a good job of our measurements, and so we've taken multiple measurements. So here are our measurements on a number line. Okay, and we haven't come up with the same measurement every time, and you can think about why that might be so. But generally, when you're carefully measuring things, you don't come up with the same measurement every time. And so now the question is, what's our best estimate of the actual height of the door? Whatever that means, right? We often call it the true value, although there are some problems with whether such a thing really exists. For example, we might need to use the height of the door in some sort of a calculation. Well, we need one number that we can plug into the calculation, but here we've got 12. What do we do? Well, you've probably already learned that you take the mean, and I hope you've encountered the mean in your previous studies. It's one kind of average. You've probably also met the median, which is another kind of average. And we take the mean as our best estimate of the true value of a measurement. And let's just quickly find it. Spreadsheets are your friend. So here is a spreadsheet, and there are the numbers from the number line, and I'm just going to calculate. We need the sum. We need to add up all of those numbers and divide by how many numbers there are, which is 12. And there's our mean, 2.2350833333333. Okay, but there will be an issue of how many significant figures we actually have there. So we just found our mean, and we're taking it as our best estimate. But of course it has lots and lots of digits, and the question we ought to be asking now is how many of these are significant figures? Now, one thing to realize is that if we were to do the whole set of measurements again, okay, so here's our set of measurements, we wouldn't expect to get exactly the same set of measurements. And so we also shouldn't expect to get the same mean or best estimate. So all we can really say is that whatever the true value, if that even exists, of the measurement is, it's within some hopefully small range, somewhere around this mean we've found. And it doesn't matter how many measurements we take or how precise our instruments are, all we can do is reduce the size of that range. So there are really two separate issues here. First of all, what's the uncertainty of each of our individual measurements? And second of all, once we get a best estimate out of our set of measurements, what's the uncertainty in that? In other words, how close do we think it is likely to be to the true value? And just to illustrate that, just here's our data set that we had before. Now suppose we get a more precise measuring instrument of some sort. I don't know, it could be an interferometer or something. And we set it up and measure the door again, and we get this data set. And this part here is just a blow up of it. So this is what we would call a more precise instrument. The measurements are more clustered. It's more consistent. And what we'd like now is a way of quantifying how precise a measurement is. And this has to do with how much scatter there is in the data. So we'd like to be able to essentially measure how much scatter there is in our data. So here's our data set again, and here's the mean. And one way of thinking about how to measure how spread out the data is to just realize that the mean is sitting right in here. And you can talk about the distance that each data point is away from the mean, right? This one is almost 2 from the mean, this one is a little more than 1 from the mean, and so on. And so we can talk about the typical distance from the mean as a way of talking about how spread out the data is, right? So that's our idea. We want the typical deviation from the mean. I'll put that in quotes. And you can think about how you would do this. Well, you know, when you want something typical, you usually take an average, a mean, right? So you could find the mean deviation from the mean. But if you think about that, a lot of them are going to be positive, a lot of those deviations, and a lot of the deviations will be negative, and they'll cancel out. And you can actually prove that they cancel out exactly, and your mean deviation from the mean is guaranteed to be 0. So another idea is you could find your mean absolute deviation, right? It would look something like you would add up the absolute values of the deviations from the mean, right? There's a deviation from the mean. I'm taking the absolute value. I'm going to add them all up and divide by how many data points I have, right? And that would be a perfectly good way of quantifying the amount of scatter. That's not the one we usually use because there's another trick you can do. The other way of getting rid of negatives, right? That's what we're doing here. We're getting rid of negatives. The other way of getting rid of negatives is to square the things, right? So if you instead take the mean squared deviation, and that's what leads us to this thing called a standard deviation, which is sort of like a mean squared deviation, except then you take a square root. So the usual measure we use of the scatter is this thing called the standard deviation. So this sigma, and I'll say sigma x, is the standard deviation of x. And look what you do. You take each of your x's, so each data point, and you subtract the mean. So you get a deviation. You square all those deviations, add them all up, and divide by, well, you're not quite taking the average squared deviation. There's an n minus 1 instead of just an n for technical reasons. Now you take the square root, and part of the reason for that is that you want an answer that has the same dimensions as your data. And if you don't take the square root, it has the dimensions of whatever your data squared is. So we're going to interpret this as an estimate of the uncertainty in each measurement because it's the amount that they tend to scatter around the mean. Let's just do that calculation. So for our data set, we can calculate the deviations. So here's a deviation. And if you know about spreadsheets, you'll know why I'm putting a $sign there. We'll discuss that in lab if you don't know about that. And there, I've just calculated all the deviations. Now I'm going to square them. You don't have to do it in this laborious way. In fact, there's an internal function in a typical spreadsheet to calculate a standard deviation. But your first few times, it's sort of useful to get to know how a standard deviation works. So now I'm going to do what the formula says. I'm going to take that and divide it by n minus 1. So I'm going to take the sum of all those squared deviations, and I'm going to divide them by, and I happen to know that this is 12 data points, so I'll divide by 11. And so finally, I'll get my standard deviation. It's going to just be the square root of that. And I'm done. 0.00124. Now we're ready to talk about the uncertainty in our best estimate. The uncertainty in the mean. What do I mean, the uncertainty in the mean? Well, look, here's our original data set right here. And let's say you took 12 new measurements. you wouldn't expect to get exactly the same measurements. You'd get a new set of measurements, but it would be similar, right? So this will not have the same mean. And the question now is, from measurement to measurement, from set of measurements to set of measurements, how much do we expect the mean to wiggle around? You don't expect it to wiggle around very much. These, you could believe these are measurements of the same door. But now, if you were given these measurements by someone else, I would hope you would look at it and say, gee, I don't really think you were measuring the same door. Look, the whole set of measurements seems to have shifted down. So here are the means of these first two. Here's the mean of the second one, of the third one. And they're so different that it's unlikely that this could be measurements at the same door. Now, some of it is to do with the scatter of the data. Here are the standard deviations of these data sets. And they overlap, but this is still too much. You don't expect the mean to jiggle around by as much as a full standard deviation. So we need something else that's an estimate of our amount of wiggle of the mean. So the thing you use is something called the standard deviation of the mean. SDOM, if you take a stats course, you might hear it called standard error. This is the thing we interpret as the uncertainty in our best estimate, the uncertainty in our mean. And you just get it, here it is, sigma x bar, right? The standard deviation of the mean is just your standard deviation divided by the square root of the number of data points you have. That's it. And now finally we can write down our answer. So we write the mean, which is our best estimate, plus or minus the standard deviation of the mean, which is its uncertainty. The SDOM has only one sig fig. It's just no more reliable than that, and you always round it up just to be a little bit conservative about things. The sig figs of the mean now you have to determine from the significant figure rule for addition, right? Because the SDOM is telling you a digit that is the last digit that you really know much about. So we had, here's our mean for the data set we've been working with. Here's the standard deviation. If you just divide that by the square root of the number of data points, that's the square root of 12, you get this. So there's the SDOM. So notice the SDOM, we would cut it off here. It's only got one sig fig. It would be rounded up to 0.0004. And then that's telling you, since it's sitting in the fourth place after the decimal point, that the mean is going to be rounded to that as well. And so there are the sig figs of the mean, although we have to be careful with our rounding. And there is our final answer.